Alright, so we've been talking about games. We talked about how we model games. We talked about matrix and simultaneous forms of games. We talked about sequential games. But all the games we've been talking about have really existed in this one-shot world. So let's go back to our game, The Battle of the Administrators, where Dean Garrett and President Wu are deciding where to hang out. And they can hang out at the boathouse, or they can hang out at Vixen's Den. But they have no way of communicating with one another. So it's a simultaneous game. We have an equilibrium concept for this simultaneous one-shot game. So what are the equilibria in this game?
Boathouse, and Vixen's Den.
The equilibria in this game are where they wind up at the same place. If they're hanging out, they want to hang out together. If they were at boathouse, no one would unilaterally decide to go hang out in the laundry room. If they were both in the laundry room, no one would unilaterally decide to go hang out in the boathouse. But the thing is, President Wu and Dean Garrett work together. They are deciding where to hang out together all the time. So maybe the way we had thought of this game, the way we had conceived of this game, is a one-shot game, is two people simultaneously making one decision, doesn't make that much sense in context. Remember, when we were modeling games, we were abstracting reality because we want to draw some insight from that reality. But maybe the abstraction doesn't have to be so severe. So let's, rather than play this as a one-shot game, play this as a repeated game. Let's get together with a partner, and there's only 5 of you, so whoever the odd person out is, I will partner up with. And let's play this game repeatedly. So that means keep playing them over and over again. And remember, our goal here is to maximize our own individual payoff. So get together with a partner, decide who is President Wu, who is Dean Garrett. We can, let's get a new pen. We can put the payoffs up here. Boathouse Vixen, Boathouse Vixen. We'll say this is Wu, this is Garrett. 1, 0, 0, 0, 1, 2. And remember, when we play a simultaneous game, and though we are playing this game over and over again, we're going to keep playing this game, it's still simultaneous. So we have no way of communicating. We're just going to tell each other what we're choosing, and we're going to do it over and over again. So partner up, you two, and everyone, I'll come over to you and partner. And just keep playing this game over and over again. So decide who's player 1, who's player 2, and over again.
Is there another marker?
You can go up and grab some. You don't have to use the dry erase board if you don't want to. Looks like you guys have decided on using dry erase board for that. Fair enough. Y'all can take this one. These two. Alright. Did you want to be player 1 or player 2?
Player 1.
Alright. So, play.
Yeah.
Write down where you go. Alright. Ready?
What is it? First of all, I'm going to do this. guess I can. Look, wait.
I was just trying to. Alright, you ready?
The vote house.
How does that
So I can choose it over and over. You get like going to, yeah, or the vote house. And then, as I remember that one. You do have to have
Ready?
Oh, yeah. They're just writing.
However you guys are playing the game works, have you gone through a couple repetitions already?
No.
Alright. So why don't you guys keep going. I'm gonna wash some of the dry erase marker off my hands and I'll be back in 1 second. Great job, everyone.
Yeah, it's are you serious? I used to go down in the first floor. One, two, three, 10. One, two, 10. Yeah, you want to it's 7 and a half. No. I'm going to make sure we get it's supposed to be good. Well, I'm the chef from here, you know. It's not how I
Alright, so it sounds like you guys have started to settle on some strategies now that we're playing this game repeatedly. Why don't you tell me about it? What did you guys end up doing? When we played the game more than once, what happened?
So we noticed like when we play it more than once that we end up picking to go to the same place.
Okay.
Because we know like we can maximize our payoff versus when we don't go to the same place.
So which same place?
So like if I pick to go to the gym, then she would pick to go to the gym, or if we pick to go to the boat at the same time.
So how did you figure out which same place to go to since you're making that decision simultaneously?
So I think it just like first, of course, she wants to go. She's senior, so of course she wants to go to the boat house, and I choose the gym.
Mm-hmm.
And then we noticed the same thing again. So this time I picked the den again, and she changes to boat house, and so I go. No, she changes to den too, and so I go. Well then, let's go to boat. We don't say this, but it's like a mind thing, I guess.
I mean, it sounds like, but I'm having some trouble following you. So what happened? Tell me what happened in the game.
So now that it's repeated, Grace?
We, after a while, we started picking the same place, and then we just kept going from there.
Great. What was that same place?
Either the boathouse or the den. Like, we would both pick the den at the same time, and we both pick the boathouse at the same time.
How did that work out?
Good.
Well, not the manner. How did it work out? How did you know whether one person was picking the boathouse or the den?
Based on our previous choices.
Okay. So explain that to me.
If I pick den, I was going to pick boathouse the next time.
So you alternated, is what you're saying. You alternated boathouse and den, and that way, since you're playing it over and over again, each person gets their preferred spot every other time, and no one is winding up at 0. You guys, it sounded, had settled on a different repeating strategy. Why don't you tell the class what you guys did?
So at first, I was scared and she was loose.
Mhm.
At first, I said boathouse, and then she also said boathouse.
Mm-hmm.
So I said boathouse the next time, but then she said den, and that meant that I got 0.
Mm-hmm.
So I thought, well, if she said den this time, then she might say it next time. So I also want to say den, because then that's the one is still more than 0. So then I just kept picking den every time. So I'd be sure to have at least one payoff.
So You guys settle on a strategy where you just pick dead every time. And in this strategy, though one person might be slightly less happy, though the Dean Garrett player might be less happy, you benefit because you know that you're never going to wind up at a 0 spot. In the strategy of alternating, it might take a while to calibrate, but eventually everyone gets on average 1.5 payoff each time. In my group, we also settled on alternating. Without communicating, we're just saying boathouse or den. We're not saying, hey, let's try this strategy. But all the players seem to coalesce around something sooner or later. Questions so far? So, Battle of the Administrators wasn't the only game type we knew. There's another game type that we talked about, Prisoner's Dilemma. Who wants to describe a Prisoner's Dilemma for us? And again, when I say Prisoner's Dilemma, I mean a simultaneous one-shot Prisoner's Dilemma.
Confess or don't confess for varying assessments.
Right? So there's two players. Players have the same strategy. It's a simultaneous game, confess or don't confess, confess or deny. Don't tell me what the payoffs are. I've got some on the slide, but there's something unique about these payoffs. What is that?
They can both choose to, there's one that they can choose and they're both getting an optimal choice, but they don't know if they're like each going to choose that, so it's probably not the choice they're going to choose.
Right. Why, in the one-shot simultaneous version of the Prisoner's Dilemma, did players choose the strategies they chose?
They didn't know what the other one was going to choose.
Did they have to? No. In a Prisoner's Dilemma, you have two players, you have a simultaneous game, and that game has dominant strategies. It's always better in the Prisoner's Dilemma to confess, to rat on your partner. It's a dominant strategy. The equilibrium outcome as a result is both players confess for, in this case, a 5-year sentence. Though this strategy is dominant, though this is a Nash equilibrium where no one has a unilateral reason to switch strategy, it's also inefficient. Julia, you're going to prison tomorrow. Would you rather go for 5 years or 1 year?
1 year.
We would rather spend less time in prison. But the way we formulated this game is a simultaneous one-shot game. Everyone is going for 5 years, which seems to be a less preferred outcome. In a simultaneous one-shot game. Let's see if that changes when we're playing repeatedly. Remember, our goal is to maximize our own payoff. So partner up with the same people you were partnering with. And let's see if we can't come up with a different outcome. And let me, while you guys are setting up your dry erase boards, just put the game up here. So. All right, cool. All right, so it sounds like you guys have settled on a strategy. Why don't you tell the class about it?
Our first time, I picked deny and she picked confess.
Mm-hmm.
But then the next time I stuck with deny and she also denied.
All right, so it sounds like the strategy you settled on was deny every time. Certainly, 1 year in prison is preferred to 5 years in prison. Kamisha and Grace, what about you? Did you guys settle on any strategies?
Ultimately, we
Chose to deny every time. 1 year in prison is better than 5 years in prison. Evelyn, in our game together, it looked like you were still confessing. Meaning you were spending 0 years in prison. So, Julia, in your game with Jade, you chose to deny. In that first round, Jade, you chose to confess. In that first round you two played together, you got 0 years in prison. What made you switch to denying?
I knew she wasn't going to change it.
Mm-hmm. How did you know?
The strategy she used on our previous game, she didn't change it, so I don't know if that would necessarily contradict it because we were already working together.
Right, excellent point. Sometimes when we have the same partner, when we know their history, it's going to change what we know about strategies. Sounds like there was something else going on though, which is you were willing to risk that payoff of -1 because if you kept confessing, Julia would start to confess as well. So you didn't want your payoff of 0 to turn into a payoff of -5. When we play games repeatedly, the outcomes we observe might change. Let's do the same thing, but this time, rather than an indeterminate ending, where I say just play it over and over again, we are only going to play 5 times. 5 times. So you can count them off on your board right now. 1, 2, 3, 4, 5. Right.
It isn't. Well, oh.
1, 2, 3, confess. 1, 2, 3, deny. 1, 2, 3, confess. Deny.
All right. So now that you've done it repeatedly, but repeatedly finitely, did anything change? Grace, what did you guys do? You kept denying. Julia, what about you guys?
I wound up switching to confess and then back to deny and then back to confess.
Okay, so a bit of a trade-off. And in our game, we confessed every time. So when we have a repeated game, but with set ending, it looks like the strategies might even change further. Let's see if we can't put some points on it, some finer points, some definitions, formalize the concept, and then maybe we can derive some new equilibrium concepts. Questions or comments so far? All right. So broadly speaking, there are 2 types of repeated games. We just experienced both. We had finitely repeated games, where the games are only played a set number of times. That's what we just did. You only played the Prisoner's Dilemma with 5 repetitions. And we have infinitely repeated games, where games can go on forever and ever. Another way of conceptualizing an infinitely repeated game is not that it goes on forever and ever, but you don't know when the end point is. So it's not forever and ever, it's not 5 times exactly, and I know this is going to be 5 times. It's, I don't know when this will end. So can you guys, in your own lives, and again, game is a broadly defined concept, but can you think of any games that you repeat, but you repeat a finite amount? Yeah, Jade.
Rock, paper, scissors.
Okay. So tell me why you said that.
Okay, actually, that's finishing your game before you do.
Hmm?
Well, I was just going to say because you can keep playing it over and over and over.
Okay. So rock, paper, scissors might be that type of game. Usually when I play rock, paper, scissors, I play sort of like best 2 out of 3, so it might be a repeated game in that sense. So we can think of it finitely. Anyone else? Can you think of any repeated games in your own lives? Remember, game just means a strategic situation, so your payoffs depend on the payoffs of others and the choices of others.
Monopoly.
Monopoly? So how is that a repeated game?
There's only a certain amount of time you can go before the other person goes broke, depending on their decision.
Okay.
And depending on the decisions you do.
So certainly some types of board games we might think of as a repeated game or an instance of repetition. Remember, game doesn't have to mean play for fun, like rock, paper, scissors, or Monopoly. Game just means strategic situation. So Jamisha, what about you? Can you think of any repeated games in your own life? Any repeated strategic situations?
I'm trying to think of activities in my life.
Okay, so let's forget we're talking about repeated games. What games are in your own lives? What strategic situations exist?
Choosing what to watch on TV.
Choosing what to watch on TV. Certainly, I watch TV more than just once. That might be a repeated game. So, Julia, you have a partner. Do you always pick what's on TV?
Mm-hmm.
Sometimes she picks. Do you have a strategy for this repeated game?
We usually just take turns.
Taking turns. That sort of happened when we were playing Battle of the Administrators. Go to Boathouse half the time, go to Vixen's Den the other half of the time. Now, certainly you didn't set out when you got the Sweetbriar to say, I'm only going to watch 85 instances of television. You're probably going to keep watching TV. So we might think of that as an infinitely repeated game. You're always going to come back and have to decide who is picking what we watch on TV. You, of course, picking Criminal Minds. I don't know what the other person likes to watch.
Oh, I have a situation that wouldn't be infinite. Like, since there's only 12 weeks, and I have this one class that I really do not enjoy going to. But there's only 12 classes. So I have to decide in the morning if I'm going to go to that class, and if I don't, I only have a certain number left to choose whether or not I'm going.
Yeah, excellent point. Coming to class is a repeated game. It's strategic. Your payoff depends on the decision of others. But it's finitely repeated. At the end of the semester, that class is over. And we can think of this a couple different ways, right? We can think of it as one course, Econ 234. We can think of it as your Sweetbriar experience being a finitely repeated game. So yeah, you might see that professor you don't like again and again and again, but at the end of your 4 years, you're out of here. That might be a finitely repeated game. Going back to the TV example, one of the things that makes it infinite is not that you plan on living forever, but that you don't know when you're going to stop watching TV. What about the rest of you? Can you guys think of any examples of repeated games in your lives? And again, it might be helpful to just think of strategic situations before we get to the sense of repetition. Watching TV, excellent point. Going to class, excellent, finitely repeated example. What else?
Well, usually work and cross-country practices at the same time every day of the week. So I have to choose, am I going to go to work or am I going to go to practice? So like, I choose kind of depending on what they need me to do at work versus like, do we have a game and I really need it at practice this week? So that could be.
Right, and because your team depends on you and your workplace depends on you, the payoffs of other people are dependent on your actions and vice versa. Excellent point. Anyone else? Any repeated games? Examples? Yeah.
Who pays for McDonald's?
Okay, who's paying? Anyone else? Broadly speaking, there are two types of repeated games. Finitely repeated games, games that are only played a set number of times. We have 12 weeks of class. Games that go on forever, or games that we don't know when they will end. And though this changes our understanding of games from these one-shot games we've been talking about so far, in general, we're still interested in the same basic ingredients. So who remembers the game ingredients we've been talking about so far? Players, payoffs, outcomes, strategies, choices, rules, information. Great job. Strategies, the strategy set that each player can choose from. The detailed action plan describing every contingency. And the way we can think about strategies is that it doesn't have to be you specifically playing. It can be a representative agent. So as long as someone, some undescribed intelligence, likes Criminal Minds as much as Julia and dislikes paying for dinner as much as Julia, they would make the same choices in that situation. Information, what's available to you. Part of information is the rules of the game, but part of it is whether or not you're observing what the other players are doing. So in our prisoner's dilemma, if they're in the other interrogation room, we don't get to see whether or not they're confessing. Outcomes, so what happens when we play each strategy? And payoffs, your happiness, your utility associated with that outcome. These same basic concepts still exist in our repeated games. But we can add some friction, we can add some new elements. Jade, when you were describing what you and Julia did in repeating the prisoner's dilemma, you noted that you had settled on a strategy when you were repeating Battle of the Administration. When we think about players in a repeated game, it's helpful to ask, are we playing the same person each time or a new person each time? So let's use this latest example of who's paying at McDonald's. If it's the same person each time, it's pretty straightforward to settle into some sort of, I paid last time, you pay this time, mechanic. But what if you bring a new person to McDonald's? Then how do you decide? And again, we're not describing any equilibrium concepts right now. We're just thinking about the different ways repeating the game can change what we're used to. We want to know the strategies available to us now that we're repeating our game. And importantly, we want to know, does repeating this game change the strategy set available to us? So Grace, you mentioned you only have so many absences in one of these classes. So the fact that you went to class last week, that doesn't change whether or not you have, let's say, 5 absences left. But if you ditch class this week, then next week you only have 4 absences left. The fact that you are playing this game over and over changes the strategy set available to you. Does everyone see why that's the case? Any questions so far? Information. So in our one-shot example, the information available to us is what that other person chose, whether or not we can see them deciding, whether or not they're in another interrogation room confessing on us, or they're doing it publicly on TV and we can observe that. But now that we have repeated games, our information set is different. Because it's not just whether they're in another room making their decision, but what we remember. So, who picked what we watched on TV last night? Do we remember? Who paid for dinner last time? Do we remember? And when we do, we saw it's fairly straightforward to settle into some sort of alternating strategy. Or when we remember how someone played last time, it's fairly straightforward to settle into some strategy of we decide the same thing every time, so nothing ventured, nothing lost. Would rather have a payoff of 1 than a payoff of 0, and I know I can continue to get that payoff of 1. Questions so far? Payoffs in repeated games is particularly interesting because we want a way of adding together our payoff each time. Now, some of you have taken Econ 101, some of you have taken business classes. So let's talk about payoffs in a straightforward way of money. Is money today the same thing as money tomorrow?
No.
No. Money devalues. So if we're repeating our game infinite time, can we devalue our payoff? Can we devalue our utility? Can we discount present utility if we're playing this game over and over again? And we'll introduce some discounting concepts to talk about it. Evelyn, is that a question? So how do we represent the fact that we're repeating these games? Anyone want to take a stab at it? What do you think might be a good way of representing a repeated game?
A chart.
A chart? Great job.
A game tree?
A game tree? Great job. A game tree is another type of chart. So remember, we can represent all games in game tree form. The cool thing about a repeated game is it's just a game tree of games, right? And if we have perfect recall, if we remember who picked that we're watching Criminal Minds last night, who paid for McDonald's last week, who ratted us out to the police, who wanted to hang out at the boathouse, if we remember these things, then we can just be in a game tree where we saw the previous games in here. So remember, these dashed lines mean information sets. And an information set is a good way of representing a simultaneous game sequentially. But if we put multiple games in a game tree, then it's just like we played the same game twice. So here we have a straightforward game with strategies C and D. If the payoff of playing CC is -1, and the payoff of playing CC is -1, then in these terminal nodes of our game tree where you played CC and then CC, you have a payoff of -2. We just added those payoffs together. Now, representing these repeated games in game tree form can be problematic in a grander sense, because look how complicated game trees get very quickly. Here we have 4 branches, and all of a sudden, this very simple game, whether you're deciding C or D, becomes very hard to interpret. So while we can represent repeated games as a tree, it might become difficult to work with very, very quickly. When we were thinking earlier of representing something like chess in a game tree form, we saw a similar dimensionality problem, where one decision quickly results in several nodes. Anyone watch the Marvel movies? Did you see in Infinity War where Doctor Strange says he looked at 14 million possibilities? That doesn't make much sense if you think about all these different possibilities as a game tree. It would have been in the trillions very quickly. When we represent repeated games in game tree form, though it can be helpful for simple repeated games, it can get difficult, can get out of hand very quickly. Questions so far? So when we have a finitely repeated game, not infinite, we know when it ends. It ends after a set number of rounds. It's relatively straightforward to define an equilibrium concept that's just the same thing as in the sequential game. If you play an equilibrium at every stage of that finitely repeated game, it should make sense that this would be an equilibrium in the repeated game. We call this a stationary strategy. We want these well-functioning properties. We want if something is equilibrium in the one-shot version, for it to look like an equilibrium, at least in a finitely repeated version. Because finite repetition is basically just a one-shot game. And we can see that when we put it in the tree, and we'll see it even more in a second. So let's go back to our prisoner's dilemma game and see why that's the case. Same prisoner's dilemma we've been working with. There's 2 prisoners. The cops put them in 2 different rooms. Says, if you tell me what your friend did, I'm going to cut you a deal. What does this look like? And let me erase this information set. It looks like a game where there's a dominant strategy of confession, which results in an inefficient but stable Nash equilibrium. Both prisoners would prefer that neither confessed and they only get 1 year in jail. But what we're going to observe in practice is both prisoners confess and they get 4 years in jail because confessing is dominant. So both confessing is equilibrium. Clyde's best strategy is to confess regardless of what Jake does. Jake's best strategy is to confess regardless of what Clyde does. Confessing is a dominant strategy for both players, so we see this Nash equilibrium outcome. the mutual best response. And remember, this is just a metaphor for a strategic situation where the equilibrium outcome is suboptimal. If our two prisoners had a way of colluding with one another, had a way of communicating, had a way of guaranteeing, forcing the other into doing what they said they'd do, we could wind up at a better outcome. So now let's see what happens when we have this finitely repeated version. Well, a finitely repeated game, like we saw when we put it in a game tree, is basically just a sequential game. It's an extended form game. And the way we solve extended form games is we look at that terminal node. We look at what happens at the very end of the game and work our way backward. So let's do that. In this example, we're playing 5 prisoners' dilemmas. We're looking forward to the end of the game. So if we are on game 5, the end of the line, what are you going to do? Why are you going to deny on the 5th game?
Because that's the best for both of them.
Is it the best for both of them?
Or you would probably end up both denying on the 5th game because once you play the other round, you'll realize like if one of you deny and the other one confesses, then only one of you will get like the 0 and the other one will get the -10. Like I feel like by round 5, depending on what you chose before, they'll come to like it'll make sense for both of them to just deny to get the 1 year.
Certainly that might be the case in an infinitely repeated game. But here we have a finitely repeated game where they know there's not going to be a 6th round. And remember, when we are formulating these games, we only care about our own payoff. Anything else we might care about, fairness, equality, justice, that's already baked into the payoff. So though in this case we formulated it as years in prison, what it is utility. So we are now in the 5th round of our prisoner's dilemma game. There's not going to be a 6th round. We have stipulated that. Evelyn, I see a hand.
I would guess confess.
Okay. So I like the way you guys are thinking, but remember, you can only control one strategy at a time. You can't control what the other player is doing. So you said deny, deny. You said confess, confess. But let's talk about what you, player 1 or player 2, is doing. What are you doing?
You're gonna want to deny to get the 0.
You're going to want to deny. You said you're going to want to confess. So let's play that out. Let's play out the 5th game. There's not going to be a 6th game. And let's use your 2 responses as a result. Kamisha, you denied. Evelyn, you confessed. So Evelyn, in game 5, you're spending no years in prison. You're going home free. Jamisha, in game 5, you said you wanted to deny. Evelyn confessed. You're spending 10 years in prison. When we have a finitely repeated game, we can just look at it as a series of one-shot games. A series of one-shot games is an extended form sequential game. And the way we solve sequential games is reverse induction, backwards induction. So what we're going to do is go to that last game and solve it. As it so happens, we've already solved the prisoner's dilemma. The solution is to confess. No matter what the other player does, you're better off confessing. And because this is a finitely repeated game, because we are only playing it 5 times, we don't have to worry about future payoffs. Thank you. So when we are on game 5, we don't have to worry that our actions are going to influence what happens in game 6. This is finitely repeated. There are only 5 games, and we've just used backwards induction to fast forward to game 5. So Evelyn, you said you're confessing in game 5. Let's continue to backwardly induce. Jamisha, knowing that Evelyn is going to confess in game 5, what are you doing in game 4? You know she's going to confess in game 5. We've solved this using backwards induction, but beyond that, she already said she was confessing.
So she's confessing the whole time?
She said she's confessing in game 5.
So,
And you know that in game 5 she's going to confess. What are you doing in game 4? Confessing. At time 5, in the last period, it's essentially a one-shot game. It's no longer a repeated game. We played all the repetitions. We are in period 5, the last game. There is no future. There's no benefit from a relationship here. We know the equilibrium outcome is to confess. If we know everyone's confessing in game 5, what do we do in game 4? No, we confess. You had it already. There's no advantage to cooperating in period 4. We've already solved game 5, and we're inducting backwardly. So now it looks like game 4 is a one-shot game at the end of a 4-game cycle. You know your partner is going to rat you out in game 5. You go ahead and rat them out in game 4. And so on and so forth till we get to time 0. When a game is finitely repeated, when a game is repeated a set number of times, we can treat it as an extended form game, a game of games, and then just backwards induce. The last game in a cycle of finitely repeated games looks like a one-shot game. There's no benefit to developing a relationship. Your payoff is already baked into these numbers. There's no benefit of being trusting. When the game is repeated a finite number of times, we have this stable equilibrium concept. The equilibrium in the one-shot game is the equilibrium in the finitely repeated version. Infinitely repeated games look different. Because with an infinitely repeated game, or perhaps more appropriately, a game where we don't know when it's going to end, we don't know what that last period is, we can't use this backward induction concept. We can't fast forward to the end because we don't know when the end is. We can come up with some equilibrium concepts, and we're just describing them now. We'll go into further detail next time. But one of those concepts is the Grimm trigger concept. So if it's infinitely repeated, what Grimm trigger says is, I'll trust you until you betray me, and then I'll never trust you again. So here we have the lifetime value from confessing. You get no years in prison for that first time you confessed, but then we're in this -4 world for the rest of time. So what we have is an infinite sum. What it looks like is -4 over the discount rate. What we're doing is just comparing two strategies. One is where you're always confessing. One is where you're never confessing. And if we can stay in this never confessing strategy, where each time we're only spending 1 year in prison, we can just calculate that infinite sum where we're adding up the never confessing area minus 1 over I. We don't have to go into the calculus here of how we get this infinite sum. But as long as I is less than 3, then not confessing in the infinitely repeated game is preferable. So again, I glossed over, this isn't a calc-based class, so we don't have to go into the infinite sum. But the big concept here is that we can just collapse a finite game into a one-shot game. We can't do that with an infinite game. Questions so far? There is a folk theorem in game theory, and the reason it's called folk is because it was not proposed by any one particular person. It's just been around for long enough and eventually got proven. There's a folk theorem that says we can escape the prisoner's dilemma. Remember, what makes it a prisoner's dilemma is the equilibrium outcome is undesirable. We can escape this undesirable outcome if we play the game enough times, in this case, infinitely many, and our discount rate is low enough. So if that future value is worth enough to us, if we're not overly discounting the future. Questions so far? So that's all we've got for this time. What we're going to do next time is in detail go over what these infinitely repeated equilibria look like. We already talked about one concept, grim trigger, where I trust you until you give me reason not to, and then I never trust you again. We're going to see if there are other equilibrium concepts that we can derive when a game is repeated infinitely many times. And remember, infinite doesn't have to mean in the literal sense of uncountable numbers going on and on forever. It can just mean we don't know when the end point is. Questions? All right. There is a problem set up on Canvas. It'll be due next Monday.